Welcome to the second of 5 Advanced Energy Efficiency Concepts and Practice lectures by Amory Lovins. I'm Ralph Cavanna. At the close of Amory's remarks, he and I will engage in a rapid-fire exchange supplied mostly by all of you from cards that I hope you will pass to the aisles, which will be collected between around 8:15 and 8:30. So please, as questions occur to you, jot them down and pass them over to the aisles where they will be collected and brought over to me, and we'll get that started as soon as Amory concludes his remarks. I have the happy task of supplying a 5-part introduction of Amory over the sequence of lectures. Tonight I'm going to get some assistance, and so I'm going to content myself tonight with telling you who will be joining me in giving you a few insights on the principal speaker this evening. And the person who's going to join me in a moment is someone who Amory specifically invited, who exemplifies the best of the values that Amory is going to be talking about tonight in a lecture on the industrial sector and its energy efficiency potential and opportunities. What I want you to know about Steve Klein of the Pacific Gas and Electric Company is, well, first of all, the Pacific Gas and Electric Company was once known as the utility of Erin Brockovich, the utility that reversed the blueprints for Diablo Canyon. And many of you remember that. But what more of you, I hope, are aware of is that PG&E today is the largest investor in energy efficiency in the world. It was recently named by Fortune magazine the nation's greenest utility, and of greatest significance, I hope, in this room, was recently the recipient of an award given once every decade by the Natural Resources Defense Council for leadership in environmental performance. And the person most directly responsible for all of that, although he would stoutly deny it, but I won't give him the opportunity, is the Senior Environment Officer for the Pacific Gas and Electric Company, and the person from whom you will be hearing next, Steve Klein. Steve.
Thank you, Ralph, for that very kind introduction, and thank you also for your sustained leadership in energy policy and climate change, both in this state and across the nation. Good evening, everyone. It's my great pleasure tonight to introduce one of my heroes, Amory Lovins. And rather than reading you his very impressive and extensive bio, and I know you've all Googled him anyway, I want to share a few personal reflections relative to our experience at PG&E with Amory. When PG&E's new CEO, Peter Darby, took over a year ago, he wanted to rethink PG&E's climate policy and understand where we were and take it to the next level. And 2 people assisted him in doing that and met with our senior executive team. One was Ralph, and the other was Amory. And it's a really important thing for us to have the insight of Amory and his good thoughts. And it's affected our climate change policy, and I think it's allowed us to lead on this issue in a way that otherwise we wouldn't have been able to. Historically, when I came to PG&E in the 1980s, the relationship of Amory to our industry was not quite as warm. This was a time in which, if you'll imagine, electricity demand was growing at 7% annually, and engineers were drawing straight lines and dreaming of power plants across the state. And something happened that interfered with their plans, and that something was a brilliant young mind named Amory Lovins. And what Amory did was to turn the industry on its head and basically say, instead of building megawatts, power plants, the industry needs to be thinking about negawatts, efficiency as a resource. Efficiency is a resource to the nation, for businesses, and for our industry in particular. And that was an astonishing change in paradigm for all of us. And it's dramatically affected our company and our whole industry, and it continues to have a profound impact. So without further ado, it is really my great pleasure to introduce Amory Lovins.
Thank you all for returning for the second of these 5 public lectures on advanced energy efficiency, this one focusing on industry. American industry is the biggest force for the transformation of the planet and the economy in the history of our species. And what it basically does is take raw materials, mainly out of the ground, process them into various primary and secondary forms, make them into stuff that may be used or not used for varying lengths of time, and then some of that gets recycled, not much as you'll see. And essentially all the physical material flows in our economy result from this activity, along with over 18% of freshwater withdrawals, 31% of electricity use, 35% of the direct use of natural gas, and 96% of coal, 24% of oil use, nearly all of, half of which is for feedstocks, and 32% of the total energy use in the country, along with 29% of the fossil fuel CO2 emissions. So you can see why I want to devote a whole evening to that topic. But there's a bit of history. In the first industrial revolution, the relative scarcity of people was limiting progress in exploiting seemingly boundless nature, and the logical solution was to make people 100 times more productive, which we did. The logic of that substitution remains valid, and economics still correctly teaches us to economize on our scarcest resource, but the pattern of scarcity has reversed. In the next industrial revolution, now getting well underway, we have abundant people and scarce nature, not the other way around. So now it's not people but nature we need to be using far more productively, wringing 4, 10, 100 times the work from each unit of energy, minerals, water, topsoil, and everything else we borrow from the planet. That is the first of 4 design principles for a world that makes sense and makes money that's laid out in a book called Natural Capitalism. You can get the book and its Harvard Business Review Cliff Notes version at natcap.org for free. And it describes a way to do capitalism that is productive use of and reinvestment in capital, not just with money and goods, but also with people and nature, with all 4 forms of capital. So radical resource productivity is the first of the 2 design principles about processes and products, and we pay particular attention to how to get expanding, not diminishing returns to investment in resource efficiency, how to tunnel through the cost barrier. The second principle is to produce things the way nature does, with closed loops, no waste, and no toxicity. Then those 2 shifts need to be reinforced and rewarded by a solutions economy business model that rewards both providers and customers for doing more and better with less for longer, creating more profit that can be reinvested back into the scarcest form of productive capital, namely nature. And the result is remarkable competitive advantage. Companies doing well by doing good, and often their biggest win is not just in saving cost, it's in the ability to recruit, retain, and motivate the best, most talented people. Most of my organization's revenue actually comes from private sector consulting, applying these principles, chiefly in industry. And here's what we have to work with. Let's just take a mass flow of materials rather than an energy balance for a minute, remembering that in the United States, the stuff that we dig up, move around, process, use, and throw away, that flow of materials that does so much harm to the planet, is about 20 times our body weight per person per day, and that only counts water returned dirty, not water returned clean. Now, to look more closely at that flow, about 17% of it is biotic resources, things we grow. 83% is dead things that we mine, minerals, for example. And that total extractive flow is 93% lost in manufacturing, but in fact 83% is lost before that just in the extractive process. And of what's left, only 7% ends up getting into products. 6/7 of that is consumer ephemerals that are thrown away after one use or no uses. Only 1% of the original mass flow is still around in products providing value 6 months after production. And then what happens to those? 98% of those get thrown away too, and only 2% of them actually return as a technical nutrient to feed manufacturing or as a compost to feed nature. So if you add up the numbers, this system of processing materials is about 99.98% pure waste, which is, of course, a vast business opportunity. And it's worse than that because so much of the waste is toxic that when it comes back into nature, it limits nature's ability to keep regenerating and producing the food and fiber, the other biotic resources we need, and indeed the ecosystem services that we can't live without. So this is a bad design. We could redesign it on natural capitalist lines, growing more, mining less, and extracting a great deal less from our stock of natural capital, harvesting and extracting much more efficiently, recapturing resources in remanufacturing and after use, radically increasing resource productivity across the board, including by dematerializing products and making them last longer, so we need less flow of stuff to do the same job. And as we design out waste, also designing out toxicity, so the little bit that comes back into nature doesn't harm regenerative capacity. In fact, we deliberately reinvest some of the profits made on the right by getting rid of waste into making natural capital even more productive, investing in nature's fecundity and diversity. And these shifts are, by the way, all encouraged by the shift toward a solutions economy business model, rewarding all the parties for doing these things. Now, I'm going to talk tonight about a particular part of this opportunity, and that is applying Principle 1, radically increased resource efficiency in industry. Buildings last night, transportation tomorrow night, and then on Thursday and Friday we'll talk about how to implement these savings and what they mean. And the amount of luscious, low-hanging fruit out there really boggles the mind. For example, in a big back-end chip fabrication plant that takes the wafers full of chips and packages them into individual chips, our colleague and teacher, Mr. Lee, in Singapore, cut the energy use in less than a year by 69% per chip, with the payback just over a year, and then went on to save even more. A world-class front-end chip fab he worked on in Singapore got under a year payback on big savings, and then the savings got so big, 60% per wafer, that it provided 80% of the energy supply capacity for expanding the output of the plant 3.5-fold. 80% of the improvements paid back in 18 months. And by the way, they did all this on a planned and continuous 3-shift operation with over 20 each of cryogenic freeze plugs and hot taps. This is with big pipes with a lot of, say, chilled water going through them, and they managed to operate on the pipes, do major surgery while the patient was in use. Quite amazing stuff. So this is low-hanging fruit that fell down and is mushing up around the ankles, but the tree, you see, keeps dumping more fruit on our heads. This is what trees do. Naturally, if these fabs had been designed properly in the first place, none of this would have been possible, but they were instead designed by the standard process that's been called infectious repetitis, namely copy the last drawings. It's the opposite of continuous improvement. Mr. Lee had another interesting experience with the Hyatt Hotel in Singapore, and the short version is that by making stuff efficient and the right size and improving design, he was able to reduce lots of fan and pump power by 92%. And that was a very rapid payback. Now, typical areas to do this sort of thing are in thermal integration, distributed and unusual kinds of power systems, designing friction out of things like pipes and ducts, integrating water and energy systems, super efficient refrigeration, heat-driven refrigeration, very efficient drive systems, that's to make shafts go around, advanced controls, and making everything the right size. Mr. Lee says of chip fabs, if we design jumbo jets the way we designed those semiconductor factories, there would be an extra set of wings and 2 spare sets of landing gear just in case. And of course, the thing would never get off the ground. The reason jumbos actually fly is that we measure precisely the loads that they are intended to serve and design them accordingly. Now, let me focus here initially on one example out of all of these, and that is just pumping systems. And the basic tools are well understood. And the first most important tool with any kind of energy efficiency is to figure out what it's worth. Because if you don't know what it's worth, you won't know how much efficiency to buy. For example, if you're in a chip fab or another kind of factory that's paying 8 cents for a kilowatt hour of electricity, and you make some conservative other assumptions, it's worth about $10 or $11 present value to take 1 watt of power use and heat release out of the clean room. And if you look at the value of saving, let's say, exhaust, or improving the efficiency of motors, you can get standard metrics that you can kind of paste on your forehead and use to guide your investment behavior. And without those metrics being right at the front of your consciousness, you and your suppliers can't properly invest in efficiency. And the information of that kind is cheap and powerful, but it's also viscous. It tends to stick to the people who have it and not flow properly to those who need it. There was a factory where we saved $30,000 the first year just by labeling the light switches. People were hesitant to try fiddling with them to see which switch controlled what because they might disturb something. Labels are cheap. There was a hard drive factory that had an idiot gauge measuring pressure drop across the big filter banks, and when this gauge went from the green to the red zone, it was time to change the filters. So I had the operators paste up 2 handwritten scales, one labeled cents per drive, and the other labeled $1 million profit per year, which is a nonlinear function of cents per drive, because if your drives start getting cheaper, you start jumping market share nonlinearly. They saved an enormous amount of money just by giving the operator that information. And innumerable plants across the world have saved unbelievable amounts of energy and water and maintenance and so on just by measuring, like measuring gazintas and gazoutas. And I'll never forget the call I got from an engineer up in the Northeast at a carpet factory, I believe. And he called me rather sheepishly and said, "You know, you told us to measure what was going in and coming out of the plant. Well, we did it. And I'm pleased to tell you, although I'm kind of ashamed it took us so long to figure out, that we were wasting umpteen million gallons of water every month because 20 years ago somebody wired a float switch backwards and the main supply tank was continuously draining and refilling to no purpose, and if we hadn't measured it would still be doing that." There's a lot of those stories around. Of course, many measurements aren't worth anything because they're done with poor or uncalibrated or drifted sensors, and very few plants are designed to measure what's needed. I'm only aware of 2 chip fabs in the world where there's a long enough clear run of main chilled water pipe to get an accurate measurement off a flow meter. That means there was never an original design intent to measure the flow accurately and therefore to figure out how much energy it's taking to make a unit of chilled water, because there was no intention to improve the design. And very few plants, even if they get the measurements right, give them to the operator in real time in effective graphics. Our colleague Peter Rumsey in Oakland had a chiller that was performing about twice as badly as the guaranteed performance, the yellow line. When measured carefully, the operation fell on all these blue lines. Up is bad, that's more energy use per unit of cooling. And it turned out that the controls on the chiller had been set improperly, and when set properly, of course, then it worked the way it was supposed to down in the magenta zone. But if he hadn't measured it meticulously, it would still be using twice the energy it's supposed to be, and nobody would have known. Here's another case where it turned out immediately from measurement that the chillers were operating less efficiently than specified. The second and third ones were turning on early because the controls weren't set up right, and the maximum load, contrary to the owner's expectation, never got to the point where they would have needed $1 million worth of additional chiller that they were about to buy. Measurement is really valuable. But, of course, the technologies you're applying to turn those measurements into savings keeps improving, and it keeps improving faster than we use it up. From 1984 to 89, the potential to save U.S. electricity roughly doubled, and its real cost fell by about threefold per unit saving. Since 1990, we've had a boom in mass production of many of the electricity-saving widgets, often in Asia. Electronics have gotten cheaper. There's been a lot of competition. The technology has improved a great deal. So, for example, compact fluorescent lamps cost 85 to 94% less in real terms over a 20-year period. Now, China alone is making over $1 billion a year of them. Electronic ballasts for the most common kind of modern fluorescent light have dropped by more than a factor 10 in cost. The most efficient lighting fixtures have gone from premium to the cheapest option. Industrial variable speed drives down in cost 83 to 97% since 1990. In fact, in many parts of the country in a competitive market, the motor dealer gives you the drive for free because it's actually cheaper than putting in protective and soft start equipment they would otherwise need that's built into the drive. Window air conditioners, 69% cheaper in real terms than 1993, 13% more efficient. Low-E window coatings, 84% cheaper than just 5 years ago. Even the delivery of these technologies, that cost has dropped by about half in one competitive market I looked at just through experience and volume. And the biggest, least exploited resource, which I began to get into last night for buildings, is design integration, which typically makes very big savings cost less than small or no savings. See, this isn't mainly about the hardware. There are a lot of ever cheaper and more powerful technologies, not to mention the wizardry of catalysis, nanotech, microprocessor controls, smart new materials, and so on. There's a lot of mundane stuff going on that you might have missed because it doesn't make headlines. Some of it is unexpectedly fundamental. I'll show these in the next 3 slides, for example. But most importantly, and that'll be the rest of this talk, there's the design revolution that puts the right ingredients together in the right sequence and manner and proportions to give a really tasty recipe of expanding returns. And if you add that to all the new technology, you get quite amazing opportunities. So let me start with mundane progress. A professor at UT Austin, Delbert Tessar, is doing for electromechanical actuators what Gordon Moore did for chips, making them standardized, cheap, mass-produced, very efficient and capable. All kinds of ways of turning electricity into motion, whether linear or rotary, can now be done with an order of magnitude better performance than they could some years ago. So if, for example, you were to equip an aircraft carrier with modern electric actuators to replace hydraulics in 12-main applications, you would reduce the weight of those systems by a factor 3, the personnel by a factor 3, the space by a factor 9, maintenance and complexity by a factor 2 or 3. Imagine saving 500 people on an aircraft carrier, very expensive. And you would save $20-odd million a year of operating cost. So the improvements here are going to roll through all of industry wherever we're making stuff move, and practically everything we're now doing with hydraulics can be done better with electrics. But there's a competitor creeping up fast in the outside lane. There's a little firm in Colorado called Sturman Industries, leader in hydraulics, magnetic valves, and actuators. And they have what they call a digital hydraulic operating system with very fast, precise digital valves. Very high power density hydraulics are then made possible under intelligent electronic control. They're fast, light, cheap, use almost no energy. It doesn't take any energy to hold the valve in position, but only to switch it briefly to the other state. It gives you integrated feedback, so you get fast closed-loop control in fail-safe design. So if you start applying this to all the obvious places, you get superior motion control. For example, if you have a robot picking up something heavy, it can start with extra force to get the thing moving, and then use just a little bit of force needed to keep it moving. And that sort of thing is a big energy saving we just couldn't do before because we didn't have the proper controls. Now let's try an example of how even fundamental areas of mature applications like fluid flow are seeing not just steady incremental progress, but a kind of punctuated equilibrium. Up in San Rafael, Jay Harmon's firm, Pax Scientific, is designing rotors for fluid motion, for pumps, fans, turbo expanders, all kinds of rotors. in a weird-looking Fibonacci spiral shape matching the minimum drag pattern of laminar vortex flow that is found throughout nature. And those sorts of novel rotor forms can significantly raise the efficiency and reduce the noise of fluid flow. For example, in computer muffin fans, of which about 1 billion a year are made, you get about a 30% increase in flow per watt, or save 10 dBA of noise, or any combination. These are starting to be commercialized now. They will fit ultimately practically everywhere we're moving fluid or getting energy out of moving fluid. And the phenomena that make this work, surprisingly, do not depend on scale or on Reynolds number. And ultimately, this may save, I estimate, upwards of 10% of all the electricity in the world. Now I want to turn past the hardware just to how we put the hardware together in industrial energy efficiency. And I'll suggest 8 ways that, that we need to question the way things are designed now. And the first is, what is the business vision and model and strategy and culture that causes us to want to do the activity we're using energy for? Why are we doing this thing? Do we need to do it? Do we need to do that much of it? Because eliminating the task is even better than doing it efficiently. And we always look at demand before supply, downstream before upstream, the application before the equipment, the people before the hardware, passive systems before active, quality before quantity. These will become clearer as I go along through examples, and more of them tomorrow. And if you do those 8 kinds of questions first, you will be able to get multiple benefits and make them compound and multiply and interbreed. You'll free up the most capacity, avoid the most capital expenditure, eliminate the most waste and harm, make the most profit, do the most good, have the most fun. It's important for engineers to have fun. But this means thinking in the opposite direction to the direction of process flow. We're used to thinking of how resources flow through the process to make a mixture of products and waste, but we need to think in the opposite direction, because that, as I will explain, makes equipment unnecessary or smaller or simpler. And if you consider the whole system together and optimize it for multiple benefits, you get remarkable waste reductions, freeing up of capacity, capital savings, energy savings. It all works better, it all costs less, because you're designing for the performance of a whole system, not the subsystem. In our own industrial practice, lately redesigning $30 billion worth of facilities in 29 sectors, we find things like this: that you can save half of motor system electricity between the meter and the input shaft of the driven machine and get your money back in less than a year, because you only pay for 7 improvements, the other 28 are free byproducts. I'll go through that in a minute. Similar returns, with saving often upwards of half the energy used to make chilled water and clean air at existing microchip fabrication plants. Whether you're talking about an oil refinery or a North Sea platform retrofit, or fixing the hotel loads on a Navy Aegis cruiser, retrofitting a big LNG, liquefied natural gas plant, which I'll give as a case study in a little bit, designing a new big Fischer-Tropsch gas to liquids plant, or a big platinum mine, or a data center, which I'll talk about later, or a chip fab, or a supermarket, or a chemical plant, even a new luxury yacht. In all of these cases, and many more, very diverse, we typically expect to save about 30 to 60% of the energy on retrofit, with paybacks averaging 2 or 3 years. And if it's a new installation, more like 40 to 90% savings, typically with lower capital cost. Now, this tunneling through the cost barrier, big savings cheaper than small savings, has now been observed in 29 sectors. And of course, it would again not be possible if this stuff had been properly designed in the first place. So I'm tired of retrofitting things that weren't designed right, hence the 10XE, or Factor 10 Engineering project, more about that in a minute, to help speed the reform of engineering pedagogy and practice through a casebook. We are used to thinking, as I described last night in the buildings context, that we're always subject to diminishing returns. The more energy you save, the faster the cost of the next unit of savings goes up, until it gets too expensive and you have to stop. But this isn't even always true with the level of components. For example, if you look at the data on motors of the most common type, up to at least 100 horsepower, actually even higher, up to at least 220 kilowatts, 300 horsepower. You find that there's no correlation whatever between the trade price of the motor and its rated full load efficiency. There should be, because premium efficiency motors have more and better copper and iron, so they should cost more to make. But for whatever reason, they're not priced higher. I don't know why, but I'll take it. The same is true for a lot of other components. If you shop in the Swedish market for industrial pumps, you can get 4 to 6, even 8 extra percentage points efficiency for free just by shopping carefully. So the motto in our shop is, "In God we trust, all others bring data." Please don't assume from economic theory that more efficient equipment costs more, because quite often it doesn't. And it really does matter if you shop. For example, if you buy this motor instead of this motor, you just saved over $20,000 present value for one motor. All you have to do is look it up in the MotorMaster software that's free on the web. That's a lot cheaper than $20,000. Now, when you combine components into systems, that's the really big payoff. Because even if they were subject, as say insulation is, to diminishing returns, if you artfully combine components into systems, you'll be able to get big savings costing less than small ones. I gave last night the example that as I add more insulation to my house, I get diminishing returns. That's just what insulation does. Until I have so much insulation, I get rid of the heating system, which costs even more, so I end up saving 99% of the space heating energy, cheaper than if I'd set out to save little or nothing. And rather than getting there the long way around, let's just tunnel through the cost barrier directly to that destination. When I worked for the inventor Edwin Land, he said that invention is just a sudden cessation of stupidity. He also said a mistake is simply a circumstance not yet turned to your advantage. And I want to rearrange your mental furniture a little with an example from our industrial friends at the Interface Corporation, which is a very large maker of carpet tiles and fabrics. And they needed a runaround loop for heat transfer in a new factory. And it was optimized by the top European firm in their sector to use 70.8 kilowatts of pumping power to move the heat transfer fluid. But then a Dutch engineer, Jan Schillem, redesigned it to use 5.3 kilowatts, which was 92% less. Some uncertainty about that number that we're still nailing down. But it was a very dramatic reduction. It cost less to build. It worked better in every respect, not because of any changes in the pumps, motors, or process or controls, but because of two changes in the design mentality. Now, the first one was to use big pipes and small pumps rather than small pipes and big pumps. You see, the friction in a pipe goes down as nearly the 5th power of its diameter. So how big should the pipe be to optimize its friction? And all the textbooks that we've been able to find say you should make the pipe just as fat as will repay its greater capital cost over the years out of the saved pumping energy, which sounds perfectly logical. I mean, you don't want to pay more than it's worth, do you? But it's methodologically wrong because it leaves out the capital cost of the pumping system. The pump, the motor, the inverters, the electricals must all be big enough to overcome the pipe friction, and therefore their size and roughly their capital cost will go down as nearly the 5th power of the pipe diameter. But the capital cost of the fatter pipe only goes up as about the 2nd power of its diameter. So if you optimize the pipe size by itself in isolation, you're pessimizing the system. What we ought to do is optimize the whole thing together, the pipe and the pumping equipment, and then we'll use really fat pipe, little tiny pumps and motors, and the whole thing will cost less to build. Now, the other change in design mentality was even simpler and more difficult, and that's to lay out the pipes first, then the equipment. What normally happens, of course, is that the tanks and boilers and so on go in some arbitrary, traditional, or convenient place, and then you call in the pipe fitters and say, please come connect point A to point B. But by then, A and B are rather far apart. Other stuff got in between. They're at the wrong height. They face the wrong way. And by the time the pipe winds its way across the space, all dressed at neat right angles like they teach us in trade school, the piping system has about 3 to 6 times the friction it should have had with a straight shot. Now, the pipe fitters think this is wonderful. You pay them by the hour. They mark up the extra pipes and fittings. They're not going to pay for your bigger pumping equipment, nor your bigger electric bill forever after. But for you as owner, it would of course be more intelligent to have fat, short, straight pipes rather than skinny, long, crooked pipes. And this gives us a factor 12 or so reduction in this case in the pumping energy at lower capital cost and with a free bonus of a 70 kilowatt saving on heat loss because it's easier to insulate short straight pipes. Oh, but I'm afraid this design got messed up because we didn't count 7 additional benefits that we only thought of later. Namely, the whole system is now smaller, it's lighter, so there's less structure to hold it up, it's quieter, those all have a value. It has a beautifully clean layout for easy maintenance access, but there isn't much to maintain or to go wrong. It's going to have better uptime, and it will last longer because you don't have all those elbows being eroded away by fluid turning a corner. And I did a rough estimate that if we'd properly counted those benefits, we would have used even fatter pipe and saved another factor, roughly 4. Sorry we left that on the table. We'll do better next time. But the more benefits you count, the better whole system optimization you'll get. Bigger savings at even lower cost. Now, this case is really an archetype because practically everything we have that uses energy was designed to optimize isolated components for single benefits. But if instead we optimize whole systems for multiple benefits, we'll typically get half to 1 order of magnitude energy and resource savings. It'll usually cost less to build, it'll work better. And my colleagues and I, led by Imran Sheikh, who's over here, are compiling, collecting practitioners and cases to put in a casebook of very high brain Velcro examples, which we hope to pull together in a summer study, perhaps as early as summer 2008, aimed at the nonviolent overthrow of bad engineering. Go to 10xe.org to learn more, and if any of you think this way or know people who do have great cases from any engineering discipline or application, we would love to hear from you and bring you into this effort. Now, notice that the pipes and pumps example I just gave reflects a very peculiar pedagogic error. And I actually had a PhD engineer go through all the main US engineering textbooks for a year to figure out what was going on here. And we couldn't find any that correctly presented 2 very basic design cases. All these textbooks said to optimize pipe diameter against the saved friction, therefore pumping power, ignoring the capital cost of the pumping equipment. And they all said also to optimize thermal insulation, say in a house, against the saved heating cost, ignoring the capital cost of the heating equipment. What's odd about this way of giving you instructions for designing, a wall or a window or a pipe by itself instead of the system it goes into, which is why we've misdesigned $9 trillion worth of houses with this mistake, is that we commonly see businesses ignore life cycle costing by counting only the upfront cost, not the operating cost over time. This is the opposite mistake. It counts the operating costs over time. It counts the capital cost only for the pipe or the insulation, but not for everything else that you need to make it work. Very strange. Why am I focusing on pumping examples? Well, because pumping is the world's biggest use of motors. Motors use 3/5 of the world's electricity. A big motor running all the time uses its own capital cost worth of electricity every few weeks. There's nothing else like that except maybe an incandescent light bulb. And you can save about half the motor energy in about a 16-month payback with late 80s technologies at a nickel tariff. But that's not the first thing to do. Let's think about this problem systematically. Downstream savings beyond the motor, beyond even the pump, are often the biggest and cheapest. So let's do those first. Minimize flow and friction first. And here's why. Here's a stylized pumping system, and it starts with, say, 100 units of coal at the power plant. 2/3 of that energy goes into losses at the power plant, and then some more is lost in the grid and in the motor and so on. And by the time you get flow out the pipe, you have less than 1/10 the energy you started with. Well, turn that around backwards. Instead of compounding losses going from left to right, think about compounding savings going from right to left. Every unit of flow or friction you save in the pipe is going to save about 10 times that much coal and cost and pollution and global warming back at the power plant. And it will also, as you go back upstream, make the equipment smaller, simpler, and cheaper. Saving 1 unit of flow or friction in the pipe saves 2.5 units or so of sizing and therefore roughly capital cost in the motor, for example. So to save the most energy and the most capital cost, start downstream. And I'm going to do that now, following some lessons from Mr. Lee in Singapore, who says saving energy is like Chinese cooking, use everything, eat the feet. And of course, Chinese food is very famous for using everything by following a good recipe and paying very close attention to detail. So let's start all the way downstream. The juiciest place to start is by asking, why do we really need all that flow? Flow that you don't need to do uses no energy. So in a certain LNG plant that I'll describe a little later, you're trying to cool methane down to minus 161 and ultimately 165 Celsius in a blazing desert. And it turns out, as I walk around this site, that the acres of cryoplumbing is covered by mainly dark gray concrete and black asphalt. So I walk around with my weapon of choice, which is an infrared thermometer pointed at the ground, and my hosts are a little puzzled why I'm doing that. Well, it's because every Celsius degree by which you cool off the site by putting stuff like white sand on the ground is going to save you $59 million present value. And we worked out with the heat island experts at Lawrence Berkeley Lab that there's probably close to $1 billion worth of savings there, 10 or 20 Celsius degrees, to be had by lightening the site, improving its albedo. And then we find the cryoplumbing is sheathed in insulation. You can argue about how much insulation there should be, and then it's all covered in shiny stainless steel. It looks shiny to your eye, except that stainless steel has a terrible infrared emissivity. So actually they would have been probably better off painting it black, although it'll work better to paint it white, and white paint costs the same as black. Or I went to an ice cream plant with state-of-the-art equipment, and there's this insulated box containing all the plumbing that you pass cream through to freeze it and make it into ice cream. And to make it that cold, sitting in the same box, there are 2 giant compressors, each with a 250-horse motor sitting in the same box. What's wrong with this picture? Obviously, take the heat out of the box and it'll stay cold better. You don't need to pump chilled water to chill a building that stays cooler because it has better windows, better insulation, better lights and office equipment. And in fact, if you substitute other methods of cooling, you won't need the chillers in the first place. For example, maybe you can get free cooling out of the air or by evaporating water in a cooling tower or otherwise. And that way, with a really well-designed system for $100 per refrigerative ton of capacity, you can get 125 or so units of cooling per unit of electricity. That is well over 10 times what the best chiller system will do under very favorable conditions. Well, we recently had a high-tech plant project where they wanted to build 22,000 tons of chillers. The number coming out of the design exercise turned out to be 0 because it's in a temperate climate. So we said, dig a hole, maybe insulate it, line it, and on the cold nights of the year, use snowmaking equipment that you buy from defunct ski resorts that were put out of business by global warming to spray slush into a big heap, which we'll call Mount Sherbet. Maybe you cover it up with something, maybe you don't. And it gradually melts during the rest of the year, and 0 Celsius meltwater comes off the bottom. You spray the return water back on top. You make it big enough, because you have cheap land in this site. And it turns out that each hectare will give you 3 million ton-hours of refrigeration at 12 Celsius, and most temperate zones have plenty of cold nights to do this with. And it's cheaper than a chiller system and well over 10 times as efficient. If it's too hot to do that, then probably you have good conditions for using solar or wasted process heat to run a stack of absorption and desiccant and evaporative cooling to get, again, about 100 units of cooling per unit of electricity. So again, less stuff to pump around. There's a lot of pumps and fans and stuff associated with cooling. Now let's go back upstream from reducing flow and friction, or reducing flow rather, to the next step, which is reducing friction. in the pipes and valves. A good way to cause friction is to have bends. How often do we see a big pump that's supposed to send something up a pipe, but because it needs a partner or it's a very important pump that needs an in-place spare next to it, they draw something like this and then build it like this. So all the time the flow has to go through 2 right-angle bends and usually 2 valves. How about doing it this way with no bends and no valves or 1 valve? Well, just because we never did it that way before. But Peter Rumsey did that at the Oakland Museum. Notice this Y joint, notice this sweet bend that then takes the pipe diagonally through the air, because Peter teaches pipe fitters to lay out supply pipes as if they were drains. There's another part of their brain that knows that if drains have right-angle bends, they'll clog. Right? So this is a really ugly and very lucrative pipe layout. It saved 3/4 of the pumping energy, and it got rid of 15 pumps that will never again waste energy in maintenance. Well, find the pipe spaghetti. Notice this little red line unfolding itself in the upper left. If that tank that it comes out of, that pipe had come out of, had first been rotated 30 degrees around its vertical axis, we would have saved 11 elbows. There's some very interesting pipe layouts you can see in these pictures. You know, whoever designed those was clearly thinking about something else. And I guess my prize for great pipe untangling is to the brilliant engineer at Stone & Webster, who in a piece of an ethylene plant went from 29 elbows to 3, and those were 18-inch stainless elbows. He was a very happy camper. Now, besides getting rid of bends, you can do a lot with surface finish. You can make any necessary bends happen gradually rather than abruptly. You can have continuous smooth bends rather than segments that have roughness inside. You can avoid elbows and therefore reduce the friction below the typical 3 to 6 times excess and get it down to pretty much a straight shot. Then you can also get rid of fittings. Fittings produce friction. Pipe layout that's pretty will not save money. If it's neat, it's probably not right. And a good way to kill pump efficiency is to have constrained entering and leaving conditions, to scrunch the whole thing up so that there's a bend or a fitting right next to the pump. There's usually space to spread things out and have nice laminar flow going in and out of the pump. And if there isn't, make it. It's worth it. A lot of people use globe valves, which should be exterminated. If they're wide open, they have 25 to 35 times the friction of a full port ball valve that's wide open. And by the way, the ball valve is 3 times cheaper, not even counting the downsizing of the pumps to cope with less friction. Ball valves give good control. Globe valves are often put in for control. Don't worry about it. Use electronic adjustable speed drives to get your control instead of throttling the flow. If you got 3-way valves, generally take them out. There are a lot of redundant valves. There are a lot of balancing valves. Peter gave us an extraordinary case today of the enormous reduction in pumping power by not doing primary-secondary pumping at the Oakland airport. You know, would you put balancing rheostats in your home wiring to make the electrons go where they're supposed to? No, you make the wire fat enough that Kirchhoff does the work. Balancing valves, similarly, are an artifact of excessive pipe friction. And if there's too much friction in one place, reduce it. The ASHRAE method, if you have too much duct friction in one place, is to balance your duct flow by putting more friction in another place. You see something wrong with this idea? Yeah. Now, once we've gotten rid of the flow and friction we don't need, let's optimize the pump, going back upstream a little further. A couple of friends of mine at the Technical University of Denmark looked at a tiny little use, circulating pumps for hot water to heat your house in Denmark. It turns out that the circulation actually requires 1 or 2 watts, often less than 1 watt. But new pumps use 5 to 10 times the power they should, and they're very inefficient, and they're not properly controlled. But in Europe, they've developed pumps of that small size that go from 5 or 10% efficient up to 40, they control them properly, and now new European building standards make that worth doing. These pumps, by the way, use about 15% of a typical house's electricity in Europe. So if you made the replacement pumps over the 13-year replacement cycle the right size and efficient, they would save about 50 terawatt hours a year in Europe. That's 8,500 megawatts of baseload plants. That's a sixth of Europe's Kyoto target reduction. Not bad for little teensy pumps you never think about. Of course, all pumps, whatever size, should be optimized for the actual measured operating conditions, because it's rules of thumb and piled up margin upon margin that destroy pump efficiency, not just choosing bad pumps. Do you check whether the pump actually runs in the conditions you think? Do you use adjustable speed drives to make it run in its efficiency bullseye and then keep checking to make sure it's still there? And of course, if your process keeps varying the load, specify pumps with a big bullseye, so even if you're a little off on the operating conditions, it'll still work well. Maybe have multiple pumps, big and medium and small, each optimized for its piece of the load curve instead of trying to do it all with one pump. And use adjustable speed drives for flexibility. Buy great pumps, they're very cost effective. And of course, then we have those biomimetic rotors coming at us, which are even better. Common pump mistakes: oversizing for flexibility. Well, make the pump the right size for what you got and design it so it's easier to put in a bigger one if you need to later. Make sure you have at least 5 diameters clear pipe run on the inlet, at least 3 on the outlet, so that the flow will be laminar enough for the pump to run as it's supposed to. Get rid of unnecessary fittings. You very often see end suction diffusers, triple duty valves, and so on that simply shouldn't be there and usually disturb the proper flow in and out of the pump. And of course, if you retrofit the system with existing piping so you need less flow through the same pipes, you are typically effectively oversizing the pipe that's already there. So without having to replace the pipe, you're reducing friction as, again, nearly fifth power of diameter, and energy use falls as friction times the cube of flow. So this is a really lucrative thing to do. Then you need to think about how the pumping efficiency affects, say, a whole cooling system. You got cooling towers and condenser water pumps and so on that, as you go toward low load, get extremely energy intensive and inefficient. Primary chilled water pumps, secondary, if you have them, chilled water pumps, chillers themselves. And by the time you get through, your whole chiller plant is very inefficient. If it goes below about half load, which it probably will most of the time because it's so oversized, then it's really inefficient. It's like trying to drive efficiently a car that has only 1 gear instead of 5. So again, multiple different size pumps, adjustable speed drive. Now, maybe the juiciest of all target zones is the motor systems and controls. And normally when you talk to retrofitters, they say, well, we'll put in high efficiency motors. Not a very meaningful term. Only the best in class efficiency actually is optimal in most cases. And they put in these adjustable speed drives which let the motor go faster or slower. And that has a lot of good uses in most applications. It's often a good idea, even if your load isn't changing much. You know, would you drive your car with the accelerator on the floor and just control speed with the brake? And what if the car were a cube law device? You certainly wouldn't do that. So both these things are often worthwhile, and they'll typically save you about 15 or 20% of your drive system electricity, and they'll cost a few cents per saved kilowatt hour. And it's worth a lot. Just 1 percentage point improvement in an induction motor running all the time is worth around $70 a kilowatt, present value, at a 5-cent tariff, more here. And it's worth a lot in practice. Here's a typical chip fab where we looked at about 1/3 of the motors, and for those for which we could actually read the nameplate, we found the red X's represented where the motors were, compared with the white dots, which were all the motors of that general type on the US market in 1996. Notice best in class minus red is a big gap, averaging 6.8 percentage points. And that was a pretty typical plant that was about 15 years old. By the way, this red X is 14 motors. This red X way down in the basement is 37 motors. Sorry about that, 40 horsepower each. So the gap between best and what we got, assuming the motors are as good as the nameplate says, was worth $1.4 million present value at a 5-cent tariff, and that was only a third of the motors in that one plant. But just making the motors better and adding adjustable speed drives misses 33 other kinds of improvements that about double the savings and cut the cost by about 5-fold, tunneling through the cost barrier. And this is probably conservative, by the way. In every Department of Energy Motor Challenge project analyzed, the non-direct energy saving benefits turned out to be worth more than the energy savings that were normally counted. What are those 33 other kinds of improvements? Well, when you retrofit an induction motor, normally folks say it's not really worth it because you have to pay for the entire new motor rather than just the extra cost, if any, of a more efficient one when the old one burns out and you have to replace it anyway. And they'll say, oh, it's a 10 or 20 year payback, don't think about it. But that just counts one benefit, electricity saved by the greater nameplate efficiency of the motor, and that leaves out 17 other benefits. It turns out that half of our industrial motors never get above 60% of their rated load. A third of them never exceed 50% of their rated load. In other words, they're way oversized because the size was marked up by several layers of bureaucracy. Who got fired for making a motor too big? But maybe you can get fired for making it too small. And it's easy to measure the size you actually need. PG&E invented that procedure. So you can often make the new motor a frame or two smaller, sometimes 3. Well, it turns out that when motors are oversized, they become less efficient and they have definitely worse power factor, and they also run faster, which wastes even more energy, say with a fan or pump flow that you don't really need. So when you put in a new motor the right size, not only can you make it more efficient, but it will save more and cost less than you would expect from comparing efficiency nameplate ratings that don't count the size effects. Occasionally upsizing is worthwhile, not very often. Premium efficiency motors are not just more efficient. Their efficiency is flatter over a range of load. They have a higher power factor, also flatter across the range of load. They run cooler. This greatly increases their life and it extends the grease life of the lubricant. And also they come with more durable bearings, which avoids most motor failures. They automatically correct any iron damage from poor rewinds done with the standard technique that causes about $1 to $3 billion a year worth of extra losses from iron damage. They're less susceptible to that damage, although there's a non-destructive method you can use that actually just avoids the whole problem. And it turns out that counting the avoided iron loss plus the sizing effects typically about doubles the savings that you get just by looking at efficiency ratings. Also, the premium efficiency motors are less heated by harmonics. They're more tolerant of unbalanced voltage in the phases, improper supply voltage. They reduce distribution losses and cooling and air handling loads. 18 benefits, not just one. But you pay for it once. So if you add all that up, you're going to get bigger savings. Of course, efficiency and motor life depend on a lot of other things too, like not putting motors in hot places or smothering them in multiple coats of paint, not pulling sideways on the shaft with a V-belt that wears out the bearings, having proper shaft alignment and lubrication practice. It turns out if you replace that fan V-belt, which is a very common thing to see, with a good synchronous belt with teeth engaging cogs, you enormously reduce the losses and the maintenance, so much that just the same maintenance pays for each saved kilowatt hour with $1 left over in your pocket. Of course, you have to watch out for the efficient motor running faster, because if you're not careful specifying it, maybe you'll lose more energy running it faster than you save by running it more efficiently. Best of all, no belt, no fan, no pump, maybe no waste heat to remove. Of course, procedure matters too. You have to have procedures in place to get the most efficient motor for the job. Install it carefully. Get rid of those sideways pulls on the shaft. lubricate right with a different culture than we traditionally have. Keep the motors cool and clean and dry and quiet, and keep measuring what you're doing, tracking it all with barcodes so you know the history of your motor. But this kind of systems analysis reveals something very interesting. If you look at the input power to motors in 1986, it hasn't really changed proportionately much, and then you factor out the distribution losses and motor-specific savings, which I'll get to in a minute. You can save more with mechanical drivetrains and so on, but the motor-specific savings are this big gap, and they, for DC motors and synchronous motors and induction motors, have lots of terms to them. We were able to scope the uncertainties and show how much you saved by accumulating all these measures. Remember, almost all of those are left out of the conventional retrofit. So what you end up with is a very large saving at very low cost. Even if you can't replace, say, the pipes in a pumping system, you can replace the throttling valves with adjustable speed valves, get rid of any globe valves, re-optimize pumps and motors, and then you also get better control of your flow. That'll improve your process. You control it digitally. And that plus more reliable motors and fewer valves improves uptime. And then you take the saved maintenance time of your smart maintenance people and leverage it into more projects. Maybe they can clean that heat exchanger nobody's cleaned for 20 years and adjust the controls so things work right. And if you do all this as a whole system package, you get much bigger savings at much lower cost. That kind of systems analysis has been done for nearly all other major end uses of electricity. Our shop did that from 1986 to 92, and you can get those from esource.com in a more friendly, condensed edition of technology atlas reports and periodic updates. Now, for the last part of my talk, I would like to run very quickly through two case studies. One is an industrial retrofit of a big plant liquefying methane into liquefied natural gas, and the other is a new data center. And I think of these as like eating an Atlantic lobster. There are these big obvious chunks of meat in the tail and the front claws, but there's about an equal quantity of tasty morsels tucked in little body crevices, like the muscles that move the legs around. And if you're a skillful and persistent lobster dissector, you can get all that stuff back too. The lobster went to a lot of trouble to grow it, and it's all really tasty. So don't leave half the lobster on the table. Now, in this particular LNG plant, the second biggest in the world, 73% of what you're using gets lost as heat, and only 19% comes out in actual useful production, as opposed to heat loss in liquefying the LNG and other functions. And you might say the tail of this lobster is the power generation, because even at a very low value put on the fuel gas, it's worth $1.34 to save a watt over 20 years. Now, if you save a little electricity in this plant, instead of having 5, 6, 7, whatever gas turbines running very inefficiently at part load to provide the power, you could have plenty of redundancy, 2 extra redundant units running only 4 turbines, but near full load, so they're much more efficient. In fact, with bigger savings, just 3 would be enough. And you can also manage loads to achieve this result by like making your liquid nitrogen at night when it's easier. You have a number of gas turbines that are not axially mounted, they're side by side, and therefore, as in naval propulsion, you can do what's called virtual trail shafting. If you want a spare turbine to be already rotating synchronously, ready to take over if this one fails, that's okay. Keep it rotating synchronously with an electric motor tied to a generator on the first one, and if the first one fails, the second one's already spooled up. You don't need to wait for angular momentum to be gained. You just put fuel into it, light it off, and have a device for handling the very short glitch in power transfer from one to the other. That's a way of, again, optimizing the turbines to run pretty near full load. We found that they were cleaning off filters with compressed air, a very, very expensive commodity, inefficiently made. We said, why don't you just put a big kind of woofer, super woofer loudspeaker there and put a fast rise square wave pulse into it. And I'll bet that puff of air blows the dust off the filter. Yes, it does. It works fine. You can turbocharge your gas turbines with water spray and with evaporative cooling. Remember, they're optimized to run at 40,000 feet in an airplane where it's real cold, not at 54 C in a blazing desert. And better still, use combined cycle, which is a lot more efficient, about twice as efficient as what they've got. And there are some renewables that could be useful in that site. Okay, the front claws of the lobster are thermal integration. This plant is throwing away 3/4 of a gigawatt of heat, mainly at very high temperatures. It's about 0.3 billion present value dollars worth of fuel at a very low cost. But that heat is so valuable. You can use it, of course, not just for useful process steps, but for making cooling, for desalinating water, and to make electricity, to eliminate furnaces and electric process heat that the plant now has. And then you cascade the heat to successively lower temperatures and milk out all the rich, meaty goodness until there's nothing left but the squeal. By the way, sweet water is very valuable to make in a blazing desert. And if you don't get all the way to sweet water, you can still make brine and sell it to the nearby salt works, which then have easier salt making. This plant used a lot of fin fans, 15 megawatts just to keep them turning to blow air through radiators. It's kind of like a giant car radiator turned sideways. And this would save $21 million just by making them more efficient. For example, you can micron mist the inlet air, again, a little evap cooling, and you can greatly improve the fin fans along with other parts of the system. I'll get to that a little later. And you can systematically recover pressure letdowns and expansions. There are places where a fluid is being reduced in pressure or expanded and can go through a turbo expander or a turbine in the case of pressure letdown to recover that energy systematically. Of course, there are the motor and especially pump improvements, proper controls on compressors, heat exchange between the parallel LNG change with propane chillers, shifting from throttling valves to adjustable speed valves, getting rid of frictions, and improving power factor, phase unbalance, painting the transformers white, whitening everything that's in the sun and has to be kept cold, including the landscape, improving compressors, mechanical systems, buildings, getting rid of compressed air or at least optimizing its use. Fin fans, I promised you something on that. They're ubiquitous in big process plants. They're a way you get rid of excess heat, which you should be actually using. And after you've put it to good use, rather than these terribly inefficient fans using basically 1940s technologies, and rather than just improving the motors and the drives, let's look at the aerodynamics because there's about a factor 5 saving there. And here's how you do it. You would have a good static regain shape on the core. You would have a really efficient fan in there with a hub-mounted, probably switched reluctance motor continuously optimized. You'd have an extended surface area, kind of zigzag set of coils underneath with misters for evaporative cooling and so on. How about a really fun example? The spherical loadout tanks, where they get the LNG ready to load into the tanker and ship halfway around the world, those are big spherical tanks, and you have to circulate the liquid methane in them continuously because otherwise they stratify and the stuff rolls over and breaks the tank. That's very bad. So what they use now is an immersed motor pump system that's 68% efficient from electricity in to motion out. Now, if you used a superconducting unit like they do in naval propulsion now, with an efficient pump, that would be 89% efficient. That would cut by 2/3 the heat released from this device, therefore the boil off, a product that you meant to sell, but now it's being wasted. And you'd leverage all the upstream savings of not having to incur the losses of making the stuff that you were wasting. Now, if you use a tiny superconducting motor and a PAX rotor, this kind of shape, making a laminar vortex flow, it will make ring vortices that sustain themselves with hardly any energy. 24 watts can circulate 4 million liters of water this way. They had an aerator that replaced 137 kilowatts with about half a kilowatt. It's an incredibly efficient way of moving fluid around. Oh, by the way, while we're at it, let's put a coat of white paint on those LNG tanks. They were painted dark green because somebody liked dark green. And then the heretical questions to ask. Is the plant more reliable than needed? Should we swing output up and down more seasonally than is done? Deliver non-liquefied gas locally at a lower pressure than the contract says because they just let it down again. They don't need the pressure. Do we have the right amount of storage? Are there better process improvements? And there are ways to cascade the cryo chillers, the really big load, several different types to make it about half again as efficient. So here's a vision of the possible whole lobster on the LNG plant. It's like a 5-layered cake. You use comprehensive end-use efficiency, especially quick wins, combined cycle power generation with direct turbine drive of the compressors plus some electricity. Off the bottom of the heat from the combined cycle, you run ammonia absorption chillers to get you down to maybe -40. You chill the process streams. You also can chill the turbine inlets if you want to make the turbines run better. You evaporatively cool the gas turbine inlets so you get rid of helper motors. Off the bottom of the absorption cycle, you can distill water and make that sweet water for use and for sale. You can do a lot of wonderful things with it with cooling towers. You couldn't get wet cooling towers before because you didn't have the water. You can do that instead of dry cooling fin fans, or you can mist them. You can feed cooling tower cool air to the fin fans. Lots more integrations to come, but you get the idea. It's just putting together the stovepipe pieces and changing a disintegrated design into an integrated design. It's not rocket science. It's good sort of Victorian engineering rediscovered. And my last example is a generic new data center, server farm. John Koomey at Lawrence Berkeley National Lab and former MING professor here, consulting professor here, has pointed out that about 1.2% of U.S. electricity in 2005, almost $3 billion a year, went to data centers, a little less than 1% of world electricity. And it's growing a bit because 2000 to 2005, we about doubled the population of data centers and slightly more than doubled power use because the power use per data center went up a little bit as well. Well, we ran with the industry a design charrette in San Jose in 2003 showing how to save about 89% of the energy used by a nominal data center and make it cheaper and more reliable. And actually, the key to the whole thing, in a sense, was efficient power supplies. We could even make the whole thing a net power producer, and a good way to get to this result also is to start charging tenants in data centers by the watt, which is where the costs are mainly, rather than by the square foot as we traditionally have. That causes people to condense more load into fewer square feet, so it's impossible to cool it properly. Now, Intel says that nominally, if you have 100 watts of IT equipment load, you have to add another 175 watts for the power supply and cooling and air handling. That number varies a lot. Lawrence Berkeley typically measures an 80 or 90% rather than 175% overhead. But these support systems for the power supply and cooling run about 75 or 80% of the facility's capital cost. So squeezing these out by starting at the root of the problem where the heat comes from the IT equipment, is a very fruitful direction. Chips are hot. You really can fry an egg on your processor. This gentleman in England did so. It took him 11 minutes, and he said it was lovely with brown sauce. Years ago, I had a small hand in the conceptual design of the first efficient desktop computer, the first one really to use an LCD screen and PC card architecture, pizza box form factor. And I encouraged them to use a super efficient power supply, which cost more, but it would be offset by an avoided fan. It was so efficient, you didn't need a fan to take the heat out of it. It was silent. You could market the ergonomics. It didn't bring air through the case to deposit dust on the chips and make them fail more often. And you could then lock the whole thing in your desk drawer and save a lot of desk real estate and improve security. So those were interesting features that made it a better deal to pay more for the efficient power supply. In our shop a few years ago, we had occasion to replace several Windows boxes with one small Linux box, a Canadian thing called a Netwinder. that nominally pokes along at a few watts, maximum 14 watts. It doesn't need a fan, it fits in a desk drawer. And it's faster and more capable than what it replaced and costs less in total than just the license fee for the Windows operating system, but it saved 99 or 98% of the energy. So I didn't have any trouble with that investment decision. It also saved lots of space. Now apply this thinking to a standard, say, 2003 vintage 1U high Wintel solution rack-mounted server, which has a 160 watt power supply in those days because it was just an 800 megahertz CPU. And it had 9 fans to take heat off the motherboard and move them out into the room where we can do dumb things with it. Now instead, if you use a very high mile per gallon chip like the Transmeta Crusoe with a very long instruction word, you can get the whole equivalent server blade down to about 16 watts with 2003 technology. Higher density, higher efficiency. You can fit 72 of them in just 9U of height. So Dr. Feng at Los Alamos put 240 of those blade servers in one cabinet. And he ended up with 5 square feet of floor, 3.2 kilowatts of load. That's like 2 hair dryers. It's 8 times denser, but close to 8 times less power than the Wintel solution. 160 peak gigaflops, 240 after an upgrade, and gets very capable if you fully populate it. And it had 100% uptime for 2 years in an uncooled, dusty hallway at 29 Celsius at high altitude where the air doesn't cool as well. Now, because this was early days for blade servers and they cost more, although in volume they cost less because there's less to them, there was a tenfold saving on the support costs, and as a result, with the 7 to 8-fold better energy efficiency, total cost of ownership went down by a factor 3 or 4. Look at the incredible parameters for this 2003 technology. It's a supercomputer. It isn't quite as capable, of course. It isn't nearly as capable as, say, the Q supercomputer with its giant cooling towers. But it runs on 2 hair dryers, for heaven's sake. And think about it. You know, there's a little comparison here. Think of that Green Destiny passively cooled supercomputer kind of like a Camry, and the Q computer like a Formula One. You'd say the Formula One car goes faster? Well, yeah, but it breaks down a lot more. If the mean time between failures for that very fast machine is shorter than your computation time, the tortoise will beat the hare. And there are a lot of problems like that, especially when you recognize it's not just the hardware that causes failures. Most of it's in software and operating error. And not only that, but every 10 degrees by which you cool off the equipment is going to roughly double its life. There's some quite good chemical physics behind this. So just having that efficient chip cuts off almost 60 Celsius degrees. It's going to make your hardware about 60 times more reliable on a hardware basis alone. Now, there are a lot of ways to cool a data center. You can reduce heat loads, generally better than free. Airside economizers, that'll take 60 or 80% of the year load in Northern California. Waterside economizers, just run your cooling tower as an evaporative cooler. Desiccant absorption, water-cooled central chiller systems. Notice how much more electricity intensive we're getting as we go down the list. This is the way we now cool data centers. It's a computer room air conditioner called a crack, and they're pretty expensive and very inefficient. But go down the street to Stanford's Carnegie Institute for Global Ecology. They have a small server farm in there, closet stuffed full of servers, and that uses the night sky passive cooling system, radiant heat going away from water trickle down the roof, and that gives 0.07 or better kilowatts per ton, even better than this waterside economizer because it gets more radiative cooling. Compare that with 1.2 to 1.4 kilowatts per ton, and you can see what a good deal it is. So how do you remove heat? Well, now that we have these dense loads in computer centers, air is not a very good way. Air holds 3,500 times less heat than water per unit volume, and water needs an order of magnitude less energy to move than air for the same cooling effect. and you can much more precisely and consistently deliver and control and heat exchange the water than the air. And yeah, you can mix electricity and water. We used to do this all the time decades ago. Many industries still do. And actually, you can just heat pipe or conduct the heat out to the backplane and then have liquid cooling there, or run a heat pipe straight up. There are other tricks you can use. But why don't we just make the equipment really efficient to start with? So you don't need to use 30 or 40% of the server energy to run fans. How about zero? And in fact, Christian Bellotti at Hewlett-Packard notes that if your device plate is rated at 75C, which a lot of them are now, that's hot enough to radiate the heat away with a proper heat pipe radiator coupling. Simple heat management. A lot of data centers are full of dead servers lying around starting to rot. Stop worshiping dead servers, put them away, bury them. Same for storage we're not using. Virtualization, you can get about a 4 times reduction by condensing different functions into the same physical server rather than having each of them part loaded doing a little bit. Put the hottest stuff and the most heat tolerant and the most unimportant to your mission up on top where the failure rates are higher because it's hotter. Put the critical stuff toward the bottom of each rack. Enable all your power management features, big savings. Use science-based specs for humidity based on what your equipment actually likes, not an assumption. Often you have one crack that is trying to dry the air, another that is humidifying the air, sitting right next to each other, fighting each other. Use variable speed drives, turn off unneeded units, demand controlled ventilation, outside air economizers, 81% saving in Northern California from doing that. And just proper airflow management in a typical data center can save about 3/4 of the cooling energy. DC power supplies. In Switzerland, they saved about half the energy. Lawrence Berkeley measured a little smaller savings. But Japanese get big savings out of this with an order of magnitude better uptime. They do it in over 10,000 installations because their main installer happens to be a telco firm. In fact, you could use a distributed uninterruptible power supply, just like a lot of laptop batteries. So altogether, summarize where we are on data centers. If you look at the overhead that you have to add to 1 unit of IT equipment usage, the kilowatts of auxiliary power per kilowatt of IT equipment, the Uptime Institute says it has to be at least 0.6, and it is typically, says Lawrence Berkeley, 80 or 90% adder on the IT equipment. And Lawrence Berkeley Lab and Peter Rumsey were saying about 0.19. Our Charette in 2003 said 0.13. Carnegie Institute for Global Ecology is about a 20% overhead. They're real close to that LBNL target, and they could get better. And I think actually a good limit is 8 to 11% overhead above the IT equipment. Huge savings. It's not hard. It's just systematic, relentlessly patient adoption of good engineering. Now, the tail of this lobster is power consumption and efficient power conversion. It's worth 20 or 30 bucks roughly to get a watt out of a data center. And there are a lot of technical ways to do that with better chips, dynamic power management, super efficient power supplies, DC bus architecture. Not difficult. The front claws of the lobster are heat transfer, heat removal, thoughtfully designed airflow, at least if you're doing it with air, very efficient air handling, very efficient cooling in the way that I've described last night and tonight, heat-driven cooling based on on-site trigeneration of electricity, heating, and cooling, system efficiency upwards of 90%. Then it's ultra-reliable, say with fuel cells, and you get rid of the uninterruptible power supply. And the other little bits of the lobster, the building envelope, the lighting. You don't even need to have the lights on if there aren't any people there. Servers don't have eyes. Running at, say, 30 to 70% range of relative humidity, which the equipment will generally be fine with. You do not need a range of 45 to 55%. Diversify according to the load, so not everything's running at once. Take advantage of thermal time constants. The more efficient the equipment is, the slower it heats up. and match the cooling to the actual instantaneous needs in different area, as Johnson Controls and Hewlett-Packard are doing. Maybe innovative fluid handling devices too. And lots of little savings multiply. If you had 10 successive steps in the chain and you only saved 10% on each one, you just saved 65% of your energy. The whole lobster then, optimized system architecture and compilation and operating system. Huge savings to be had there. How many unnecessary processor cycles do we have because of bloatware and bad code? A friend of mine was recently shopping for a thin Sony laptop computer. He said that running the previous best known operating system, it would get 6 to 11 hours of operating battery life, and running the newest one, it would get 2 to 5 hours. There's something wrong there. So more useful operations per instruction executed, optimally share and spread the real-time varying workload around the data center. Why is it that our data center's electric load is constant while the workload varies upwards of threefold? That means we're not properly having the equipment follow the load imposed on its data processing. Radical, comprehensive efficiency in devices and systems, great heat transfer at each stage, on-site trigeneration with heat-driven cooling, no uninterruptible power supply, and you can make the whole data center into a net exporter of electricity that way rather than a huge burden on the distribution system. Just to end with, there are, I think, for a very long time to come, probably upwards of a century, no limits to rapid gains in profitable industrial energy efficiency. Start just by remembering that industry processes materials. That's what it does. And this is a 99.98% waste materials flow. So most of that waste is ultimately going to be turned into profit. We'll make dematerialized products, we'll virtualize more functions, we'll make things last longer, we'll close materials loops, do industrial ecology, probably desktop manufacturing without waste. Then there's conventional technological innovation that, despite the neglect of R&D, is still continuing rapidly. There are important new kinds of processes like microfluidic processing that can often reduce a large chemical plant to about the size of a watermelon. End-use efficiency keeps getting bigger and cheaper, especially with integrative engineering to tunnel through the cost barrier. And now coming at us, two further design revolutions: biomimicry, Janine Benyus's work on innovation inspired by nature, and maybe molecular assemblers, Eric Drexler's original nanotechnology concept, which is not what is nowadays often called nanotech, and it's not biotechnology, which is often a bad idea because Darwin always beats Descartes. And then there's stuff we haven't thought of, but we could live to do so if we are pretty quick about getting the hang of responsibly combining a large forebrain with opposable thumbs. The jury's still out on whether that was really a good idea. I think what I've described is just good, simple engineering. No inefficiency, engineers have been at that for millennia, and no incrementalism. That's where we need to go now, because we have met the enemy, and as Pogo said, they are us. Thank you.
Before subjecting Amory to a very brief cross-examination given the hour, I'm going to make an observation that I know he joins me in. Amory is here this evening as the Matt Ming Visiting Professor on Energy and the Environment, as I mentioned at the outset. That title, while distinguished, contains within it a reminder that Amory is unable to spend all of his time overcoming the educational deficiencies he is bemoaning this evening. And he and I share a delight in the emergence over the past year of the Precourt Institute for Energy Efficiency at Stanford, headed by Jim Sweeney, who is here this evening. Now, all of you who know Jim know that he will not rest until Stanford is universally acknowledged as the international leader in energy efficiency, innovation, and commercialization. And he will need some help in getting there, and Amory and I ask all of you to join us in doing whatever he asks to secure that very important objective. In that spirit, Amory, a couple of questions suggested by your remarks. First, a questioner was fascinated by all the inefficiencies you found in an typical LNG terminal, and wonders if collectively, absent the Lovins treatment, they mean that LNG is actually less efficient on a life cycle basis than electricity generated from coal. What is your view of that?
I'm not sure what sort of comparison of efficiency the questioner has in mind.
I think the questioner has in mind we're importing LNG into California to make electricity to displace coal. Is that a good idea?
Well, I wouldn't do either one. It's one of those "are you still beating your wife" questions. LNG needs probably $3.50 gas onshore or $4 for safety, as it should be sited offshore. And for less than a quarter of that price, we can save half the gas in the country, and then LNG's market disappears several times over. So I think anybody who puts money into LNG is very much at risk from the huge overhang of unbought efficiency. And of course, coal-fired and, for that matter, nuclear power plants are so uneconomic that they have under half the world market in electrical services now. A third of that market has been captured by micropower, and another roughly comparable chunk by negawatts, because they have lower cost and lower financial risk.
Amory, your charts of materials flow and the extraordinary amount of waste involved in the typical industrial process prompts questions from two ends of a spectrum. One is to ask whether hidden subsidies for waste disposal are part of the problem and what might be done to remove them. The other is to ask whether you think curbside recycling is worth the time and trouble. Please take them in turn.
Oh dear. I expect there probably are subsidies to those mass flows. There are certainly big subsidies on the front end to mining, and often folks are allowed to kind of dump stuff where they shouldn't be. Waste disposal costs have, however, been starting to approach their proper marginal value in many cases, and that is indeed, in the case of wastewater, the main driver behind California's nearly doubling its water productivity just in the 1980s. It wasn't to save water, which was still generally cheap and subsidized, but to avoid wastewater disposal costs. There is vastly more to be done on those lines, and some of the companies we work with have already cut their material waste flows by upwards of 70% at a huge profit. In fact, just in demolishing buildings, there are reductions commonly achieved upwards of 90%, even in the high 90s, at zero or negative marginal cost. That is, you typically make as much money recovering the stuff and selling it on computer bulletin boards for reuse or through exchanges of such materials as you pay for the more careful demolition, because of course you also avoid landfill tipping fees. Curbside recycling is a much more complicated question because it depends on what happens after that. Not making trash in the first place is always the best solution, but many of the curbside recycling programs are well run and should indeed continue.
And I think I will close this evening by asking you, Amory, a big picture question from a member of the audience who, impressed by your sustained optimism, wonders if you think we can stabilize greenhouse gases in the atmosphere at safe levels at zero net cost. Is that an assumption we should all take from this presentation?
I would say at negative net cost, and yes, you should. I will give you the numbers on that on Friday. And we have actually a very conservative but very instructive new supply curve on exactly that question from McKinsey, showing an approximately zero net cost abatement of half the world's greenhouse gas emissions. But it is so conservative technically, I think it leaves out most of the good stuff, a lot of which is in transport, as I'll describe tomorrow night.
Tomorrow, Amory will take on the small matter of transportation. Please join us then, and join me in thanking him this evening. Thank you.
Oh.